Well, thank you for hanging out through the technical difficulties of getting two monitors shown up. So I would like to share with you today some of the advances that have been going on the educational front of the Wolfram Alpha chemistry team. And so we'll step our way towards, hopefully, chemistry mastery, and with an allusion towards the step-by-steps that are offered through Wolfram Alpha. So the step-by-step offerings have been growing since they started back in 2013. And what I'd like to emphasize is that, as you see in the middle, we've got a simple word cloud of the various areas that we're covering at the moment. Not surprisingly, since a lot of chemistry is done in solution, most of our chemical solutions, the reactions, concentrations are the areas that we've been growing. But we're trying to cover all of the areas of chemistry, being that chemistry is a central science. So if you're in astronomy, if you're in engineering, if you're in biology, wide variety, health professions, all those different areas have to have some sort of chemistry background. And so we're trying to lower the barrier for understanding chemistry by the offerings that we're doing with the step-by-steps. And we're making very purposeful choices to try and use every educational opportunity that we have when we're doing the different steps to show what is going on from the chemistry perspective, help sort out the math, because sometimes that can be a barrier in and of itself. But we're trying to be able to have content that would support chemistry ranging from the primary school to secondary school, all the way up through college, and possibly even into the research environment, depending on what you're researching. So one of the things that has been happening in the chemistry curriculum over the last 5 to 10 years has been a change in how we talk about solving the problems. And let me see if I can make that just a bit larger. Where'd it go? Well, anyways. So what has been going on has been in past, and possibly many of you, if you happen to have a chemistry course, back in the day, the problem was stated, and then just the answer was worked out. There really wasn't any details of thought of thinking as a chemist, the problem-solving steps explicitly, how to plan what information you might need, and how you would combine it together. It was just laid out. Well, that has since changed as we've been, as the community of chemistry educators has been trying to emphasize thinking like a chemist and laying out the problem-solving strategies more explicitly. And to support that, we have started to implement what is shown here as the plan step. So these are 4 examples from working on Alpha right now, where for the different problems we stop and say, after restating the problem, we show what is going on and how one might think through the problem before we actually solve it. And again, this is so that our material will complement that which is in the modern textbooks these days. One too many. So let's pop over to an example. I have on the screen, for those that view this later on, a static example. So we'll pop over here and we'll look at the mass composition of an antihemophilic factor molecule. It has quite a few atoms, so that makes it a little interesting. But if we click on the step-by-steps and do a little bit of scrolling, we'll request all of them. And for those that have used the step-by-step feature of Wolfram Pro, this may look familiar, but again, here we restate the problem. The new bit that I was talking about are the plan steps, and we're slowly rolling this out into all the new features that have been coming online since roughly March of this year, and we'll continue to roll this out into the existing step-by-steps as they refresh their look and expand their functionality. In this case, we're looking and counting the number of atoms. I won't walk you through the actual details of things. I did want to say and also point out here, when possible, we've also been implementing check steps. So in this case, we're dealing with fractions. And so the fractions that we've computed in this step should always add up to 1. And so we explicitly take time to show that. And we have a show details, or the show intermediate steps, that one can click and inlines the steps to add all those fractions together. So again, purposely making sure that we take advantage of every educational opportunity to clear things up for the students who might be tackling the material. Now, if we pop back over to Mathematica, One of the other things that anyone who studies in the sciences, but particularly in chemistry, will run into is the area of precision with measured values. So you go to the laboratory, you take a mass measurement, you take a volume measurement of a solute or a solvent. You need to keep track of that precision through your calculation. And in the colloquialisms in the chemistry literature, it's called significant figures, or more formally, significant digits. And since this is a barrier for many folks when they're getting started, or when you're trying to worry about all the details of just doing the calculation, you can get a little turned around with carrying around your significant figures. We've put together a Wolfram function repository function called significant digits. It's in review, so hopefully in the next few weeks it'll be showing up on the Wolfram function repository. And some of its features that it can do is that when you provide it, in this case a list, we can handle text numbers, we can handle integers and real numbers, of course. We can handle numbers in various scientific formations. And this last one here, if you're not familiar, is the ISO specification for uncertainty. So we get 4, 5, and 6 are the significant digits. This is the uncertainty here in the parentheses. More details of that. We can, there we go. Again, it's a way of keeping track of precision in measured quantities. By default, we have that all non-zero digits and zeros between non-zero digits are significant. This follows the NIST and international standards on the subject. Zeros employed to position the decimal are not significant. So numbers like 100 presented as an integer would only have one significant digit. The user has control over counting those other zeros as significant because that's context information that one would need. But all of that is built into the function. And like I said, will hopefully be available on the function repository shortly. Since significant figures are so important in the chemistry problem solving that you run into in definitely the high school and college environment, we've been trying to make all of our step-by-steps more significant figure compliant. And here, again, we have an example of the technetium fluoride for our molar masses. Since we're pulling information from the isotopic the elements and their isotopic bits, we can click on the step-by-step. And again, we're going to get all the steps. And so as you see here, let's see. Again, we have our plan step. We have the chemical formula. And then from that, we do the element tally and grab our information from the periodic table. Note here that we're keeping all the number of sig figs that are available. So even though technetium is known to quite a few number of significant figures, I believe 11, and then technetium being radioactive is only known to 2. So in this case, we lose quite a bit of precision when we do the calculation, the final result being 193. But while we're doing the work, we keep all the intermediate significant figures as you were taught to do in the classroom. So again, trying to align our step-by-step efforts with the current pedagogy in the classroom. So some other more in development stuff that I'd like to show you now, so we're not going to be able to pop over to the web to show you the actual result. We've been updating, again, our current offerings to bring them in line with modern teaching standards. So here, we're doing a simple conversion. We're going to go from grams to moles. It's a common conversion that's necessary. And as you can see, we restate the problem. We don't have a planned step here. They'll be coming out eventually, but we're still working through this. But if we were live on the website, this second step here would have an option to show more details. Before we go and show what that looks like, I'd just like to point out one of the things that we have been implementing across is a sort of fence notation for dimensional analysis where the grams are laid out in the proper fractions so they cancel out in the common way that is taught. So now if we, let's see, we'll just go down here. As units? Are you multiplying them together, so grams times moles?
Moles delineated in grams, so gram moles. I've tried using pound moles and working in pounds, but it doesn't recognize what a pound is.
I don't think we've taught it about that, but if you'll see me afterwards, we can talk and get that into the works.
Did you find a bug for them?
I was going to say that would be the fastest thing to do is if you put it into Wolfram Alpha, at the bottom of the page is a submit feedback. Click that button and fill us in, and that'll get the chemistry team and the unit team working on that right away. But feel free to talk to me afterwards. So if we clicked more details, now what you'll see is we have calculate molar mass, and again, you'll start to see the pieces that we saw when we were calculating the molar mass before. So again, this is a consistent pedagogy throughout the whole system. The steps that you saw before when calculating the molar mass are now the steps that are shown here, which you may need a refresher on as you're working through this particular problem where you had to calculate the molar mass as well. Once we have those concentration conversions, we can start building upon them. In the case of chemistry, this is moving on to doing concentrations of solutes in solution. So now we're doing the molarity. And here again, we restate the problem. This one has a plan step. And then we follow through on the plan step to show what's going on. Now, in this particular case, I'm not going to show you the details of this mass to moles conversion. It's exactly what we saw in the last show detail step. But what I'd like to show is that how we're, again, doing the fence notation to cross out the units for the student. And then also in the bottom here, we take the opportunity where we have moles per liter. We write it in a variety of forms, as the fraction, as the fractional unit, and then also using the symbol capital M for molar, which is the shorthand notation that's used quite commonly. So now if we can compute the molality or the molarity or the mass fraction or any of the other concentration units which we have working live on the website, we can start to go the reverse direction and say, using those definitions of concentration, can we create recipes for solution preparation? So if you're working in a laboratory and you're tasked with creating a 2 molar solution of an acid or a half a millimolar solution of whatever, we have steps that now are working through helping you solve that. Again, we have a plan step, and as in so many problems, you have to immediately convert grams to moles. And then here, we're going to bring the molarity over to the units that we need for canceling out. And then here, in this step, we're going to use an existing definition, in this case, a definition of molarity, and we're going to do some algebra to rearrange that. Now, sometimes that algebraic step is quite simple and straightforward for those that are at this point in their career, but maybe that isn't so straightforward for them. And what we have set up is that when this goes live, oh, come on. What we've got now is set up that we use the math step-by-steps to take care of their symbolic algebraic transformations, and the student then can see doing the algebraic manipulations to get the, in this case, isolate V on the left-hand side. So we both, in the step-by-steps for chemistry, have additional details on the chemistry side and additional details on the math side, all in support of doing the final chemistry problem at hand. Supporting all of this has been some great efforts by our video team. They have been putting together tutorial videos to help both the students get familiar with using the tools in the classroom and also as resources for the educators to put into their learning management systems so that they don't have to spend precious classroom time on teaching the students how to use the software. So if you'll indulge me, we'll pop over and I'd like to show you those videos right now.
Welcome to Quick Takes with Wolfram Alpha. Let's look at how to balance a chemical equation. Give the name or chemical formula for each reactant and product in the reaction, with an arrow in between the last reactant and the first product. For example, type carbon dioxide and H2O as reactants. Then type the arrow using the extended keyboard or a hyphen and the greater than sign. And finally, type O2 and glucose as products. Now press Enter. Wolfram Alpha will compute the answer. The first thing that Wolfram Alpha generates is the interpretation of your query. Make sure that this is what you had in mind. Otherwise, more detail will be needed. With a Wolfram Alpha Pro subscription, the step-by-step solution is provided in addition to the answer. You can study steps one by one or all at once. Wolfram alpha also generates other useful information, such as chemical names and their properties. If only reactants are provided, for example, sulfur and O2 produce, Wolfram alpha generates some possible reactions containing those reagents. Check out the rest of our videos for more tips on how to get the most from Wolfram alpha. Thanks for watching.
So that was our reactions balancing, which is a critical part to most chemical reactions and chemical problems. And then here's the other
Welcome to
building
Quick
on
Takes
that.
with Wolfram alpha. Let's look at how to do stoichiometry. Give the name or chemical formula for each reactant and product with an arrow separating reactants from products. For example, glucose plus O2, arrow H2O plus CO2. You can type the arrow using the extended keyboard or a hyphen and a greater than sign. Then provide the amount of one or more molecules in terms of mass or the number of moles. For example, 0.1 mole glucose. Now press enter. Wolfram alpha will compute the answer. The first thing that Wolfram alpha generates is the interpretation of your query. Make sure that this is what you had in mind. Otherwise, more detail will be needed. Wolfram alpha generates the balanced chemical equation and does stoichiometric calculations to provide the yield, along with the amount of other reactants needed. With a Wolfram Alpha Pro subscription, the step-by-step solution is provided in addition to the answer. The steps can be studied one by one or all at once. If the initial amounts of 2 or more reactants are provided, for example, 0.1 mole glucose plus 10 grams O2, arrow H2O plus CO2, Wolfram Alpha identifies the limiting reagents in addition to providing the yield and the amounts of other reactants necessary. Additionally, if the amount of any product is given, for example, 0.1 mole glucose plus 10 grams O2, arrow 5 grams H2O plus CO2, Wolfram Alpha computes the yield percent too. Check out the rest of our videos for more tips on how to get the most from Wolfram Alpha. Thanks for watching.
So we hope that these videos will not only, like I said, make it easier for students to get into using our software, but also for the educator to bring it into their classroom. And these videos will be translated into a variety of other languages with captions, and will be available on the YouTube feed for the Wolfram Alpha in the upcoming weeks. These videos, along with others that we have in planning, will keep coming out over the next few months to, again, increase the offerings. Now, this slide is rather busy with all the small details and is intended for those folks who might be watching this later on after the conference. But what I'm trying to show here is that we're working on sig figs. That connects into just about every calculation that we've got going. We're working on solution concentrations, which are setting us up for the necessary bits to do equilibrium constant calculations, to do pH calculations, to do buffers, titrations, and the more cumbersome, possibly sexier calculations that you might do further on in your advanced courses. But we're building up and cleaning up the machinery that we have now to tackle those things, in addition to following tracks that will eventually lead us up to doing molecular orbital diagrams and things coming out of the quantum side of the curriculum as well. So just to finish off, I've got links to all the things that I was talking about. The How to Use Wolfram Alpha YouTube playlist is up at the top. The step-by-step example page for chemistry is there second. Also a link to the chemistry functions in the Wolfram Function repository. And then we have links to the molecular structure and computation that the other team member from the chemistry team talked about, and a link to our chemistry entities to see what's there. And I should, as I said, I am not the only member of the chemistry team. It is a group of 5 of us, and we are working very hard to make chemistry more exciting and accessible to everyone as they use Wolfram Alpha. So at this point, if you have any questions, I'd be happy to answer them, and thank you for your attention.